I hope everybody got some caffeine out there, so they're awake. I got my caffeine. If I'm talking a little bit too fast, just raise your hand, tell me to slow down. But we're going to change direction a bit after the break here. Those first three talks that we had were really focused a bit more about why RISC-V and an introduction and history and ecosystem and just questions like that. So we're moving off of the sort of abstract why RISC-V, and we're going to assume here that you've made the decision to go with RISC-V. And so what are you going to do now? And the first thing that you're going to do is figure out what you're going to do about a RISC-V processor. And this is a more or less classic make versus buy decision. So that's what we're going to spend the next few minutes talking about. So I'm from Imperas. Imperas does not build RISC-V processors. We're actually a tool company. We build models, we build simulators, we build other IP. So why am I up here talking about processors and make versus buy? Well, I'm up here because we see nearly every RISC-V project and processor. It doesn't matter whether it's a make or a buy decision. We're going to see pretty much everything. We don't care what your decision is. We don't care at all. We have relationships with nearly every major RISC-V processor vendor. We participate in the open source projects. We have customers that are building their own. So we don't really care. What we do care about is that when you make the decision, you do it with appropriate thought and care going into that decision. So I will give you just a quick pitch here. What do? We start with models. We've got models of the full RISC-V spec, including the stable unratified versions, and you can add custom instructions to that. That becomes a reference model. That reference model can be used for verification, something really important in the RISC-V world. Can also be used in a virtual platform or software simulation environment for software development. So that's Imperas. We're models, we're tools. And actually, as we've talked about adoption and where RISC-V is going, one of the interesting things in this last month leading up to the RISC-V Summit is that in the tools area, we've seen Synopsys, one of the major EDA players, not only join the RISC-V International Organization, but join at a premier level. And so Synopsys is actually investing in RISC-V here and sees the opportunity as a tool provider to support the RISC-V community. So I said we see most projects. So we've got a nice customer list there. We've got a list of processor IP partners. We've got tool partners. In the bottom left, there's this thing called RISC-V OVP Sim Plus. It's a free instruction set simulator that we provide, and there are more than 100 organizations using the free tools, plus our commercial partners. So there's something like over 150 different RISC-V projects that we've seen. So on to RISC-V, enough of the commercial. So RISC-V is an open standard instruction set architecture. We heard that this morning. The freedom enables domain-specific processors. That's a key piece of this, and it's the freedom and not the free that is driving and accelerating the RISC-V adoption. So what are the sources of implementations, of the RISC-V processor implementations? Well, we've talked about processor IP vendors, Sci-Fi, Andes, Codasip, and down the list there. There are also open source implementations. Ted mentioned a few of those, like Low Risk and Open Hardware Group. And then you can build it from scratch. And there are organizations that are absolutely going and doing that. But the thing that we see because of the freedom in RISC-V is that with all these implementations, custom instructions and configurations are going to be used. And then with all these implementations, even with well-verified processor IP, the processor plus the custom features must be designed and verified. And then don't forget about the software cost for the tool chain, for software porting, for the other software side of it. So there are a whole bunch of factors that need to come into this decision about which processor or how you implement the processor. So in no priority order, we can look at IP ownership. Do you own the IP or are you licensing the IP? If you're licensing it, what is the licensing cost? And then the PPA, what is the power performance area for the core? So that's one category or one set of factors. And these are actually relatively easy to estimate, these costs and benefits. But now there's some other things. If you're going with open source, if you're going to build your own, what are the resource requirements for the base processor? What's the cost of adding custom instructions? What's the cost for the design, for the verification, for the tool chain, for the software porting? And there are other costs, other factors that go into this as well. With these costs, though, this is much more difficult to estimate. So this is where the care comes in. This is where you have to think through these things and figure out and do these trade-offs between the custom instructions that you're adding and the resource and the other costs that it's going to take to implement those. So sources of processor implementations, there's a partial list of the processor IP vendors. There's open source implementations. There's build from scratch, and I've listed a few companies that are public about what they're doing with RISC-V. Ted showed that landscape chart, and it's up on the RISC-V website, so feel free to start there. There's also the RISC-V exchange that Ted showed in his talk. So there are a number of resources that you have to go and look and see who's doing what. So taking a look first at processor IP vendors and the pros and cons of choosing one of the processor IP vendors. So there are lots of choices. I listed, I think, maybe a dozen in that previous slide, but I think if I count them up, there are probably closer to 36 different processor IP vendors in the RISC-V community. That actually is quite a few choices there. And there are lots of choices for different feature sets, for the PPA trade-offs. There are even different business models between the different processor IP vendors. So that gives you lots of choices, and given the number of vendors out there, gives you a bit of leverage when you're choosing your processor IP. That's a good thing. So on the con side with processor IP vendors, yep, you're paying for a license. Okay, that's fine, but you're getting processor IP, so there should be value for the license cost that you're paying. And then depending upon who you're working with, it may or may not be easy to add custom instructions. And again, adding the custom instructions, custom CSRs, it isn't just adding them in, it's supporting those and what you're going to have to do with those. So you need to think about all that. But having said that, there are a lot of processor IP companies licensing a lot of RISC-V processor IP to a lot of SoC developers. So this is certainly an easy way to go. I think John, in the first talk this morning, said that Sci-5 had something like 350 design wins. That's a lot of processor IP to a lot of SoC developers. So certainly the processor IP vendors are a viable alternative. And just as one example here, we've got MIPS. MIPS had their traditional MIPS architecture. A couple of years ago, they switched over from that MIPS architecture to the RISC-V architecture. Mobileye has actually long been a MIPS customer, and probably their major customer. And Mobileye went right along with this switch. Actually, I have to believe here that these discussions, that MIPS didn't make this decision in a vacuum, that Mobileye knew exactly where MIPS was going when they made this decision. And so Mobileye, who probably has close to 50% of the ADAS market, something like that. They're a significant player here, and they're going with RISC-V for their next generation IQ SoCs. So this is a pretty significant endorsement of RISC-V by one of the major semiconductor players, and this is actually in automotive. That's pretty significant. So that's processor IP vendor side. Let's go and look at open source implementations now. So on the pro side, there are, again, quite a few choices. I listed a handful up there. I think Ted had maybe a few more. But there are also some companies or consortiums that have collaborated and put the effort into it. It isn't just sort of open source where some grad student has said, oh, I designed a processor, I'm going to put it on GitHub, call it open source, somebody can go and download it. These are actually serious open source projects. Low Risk is one, Open Hardware is another. There are a few others that are out there. And actually, I think T-Head is another significant one. So on the con side, depending upon what this is, sometimes there's a lack of support, including user documentation. So it's unclear with some of these open source projects how well it's actually been productized, if you will. It's also not always clear how much verification has been done. With the Open Hardware Group course, actually, that is pretty clear. Again, because of that lack of documentation, if there is such a lack, it may not be as easy to add the custom instructions, CSRs, et cetera. And then there are the resource costs with open source. Just not knowing exactly what you're getting there in some cases. What do you need to plan for in resources? So as an example here, I'll use Dolphin Design. A company that probably none of you have ever heard of before. They're a small company based in France. They build system IP. They provide design services. One of the pieces of IP that they build is a DSP subsystem. So they're starting with Open Hardware Group cores. Open Hardware Group is a consortium with a mission to build industrial quality open source RISC-V IP. The CV32E40P V1 has gone through comprehensive verification and has been implemented in multiple SoCs. That project was initially led by Silicon Labs. Actually, still currently, Silicon Labs is working on variations of that processor. But Dolphin needed more for their Panther DSP subsystem IP than in the V1. And so they've iterated that, and they're on this V2 project. It has DSP-like capabilities. It's higher performance. It's lower power consumption. It's a smaller code size for the software running on it. And then in addition to the public open source improvements to the E40P V2, Dolphin is adding custom instructions. So they're doing this thing where they're working in the consortium to add things that they think are helpful to everyone in the consortium and even in the community, but then they're adding their own proprietary custom instructions onto this. So yeah, they're making an investment in design, in verification, in the tool chain, in the software porting, but they thought that this was the best approach for them to start from a good base and then add their custom instructions in. They thought that this was the best trade-off for them in terms of features and resources and what they were going to get out of it. So that's another one of the ways that we can go on this. And then build from scratch is the third way, the do-it-yourself processor. So you can do almost anything you want functionally. That's a pretty cool thing. That's RISC-V. It's all the different extensions that we have with RISC-V. It's all the different subsets of those extensions. You can do almost anything. If you have the expertise, you can build a more optimized microarchitecture. So that's a pretty cool thing, because if you look at Andes or Sci-Fi or Codasip, or you may be able to do something better from a performance or power consumption perspective. If you already have a proprietary ISA, switching to RISC-V reduces the business risk. Our first customer at Imperas, our first RISC-V customer, so we existed well before RISC-V. We support many other architectures besides RISC-V. But our first RISC-V customer had a proprietary architecture. And when we asked them why they were switching to RISC-V, they said, well, it's going to be just as easy or just as difficult to build the processor. But actually, we only have one guy in our company that works on the compiler for our proprietary core. And if that guy gets hit by a bus crossing the street, we are in deep trouble. But now, because they're part of the RISC-V community, they've got a whole ecosystem that's supporting them. And that's what's happening with teams with proprietary architecture. You can look at what NVIDIA did as well. You can look at, I think Seagate is another one. There are a few others that have switched from proprietary architecture to RISC-V. They had the processor expertise in-house. They just wanted to reduce their business risk. So there's no license cost here. There are no concerns about open source quality. But on the con side, you're paying for it in resources. You have to do everything. And it hasn't been tested. So if you're getting an open source core, if you're getting a core from from one of the processor IP vendors, they will have been testing it. Likely there are going to be other users of that core, and so it's going to have some additional testing there. But if you're building it yourself, you're building it yourself, and you have to trust your team on that. And I mentioned Seagate before. Seagate, this is actually an announcement from the summit 3 years ago. Seagate actually produced two different RISC-V cores, one optimized for area, one optimized for performance. They also had different functionality in the cores. One was more for moving data in their hard drives. One was more focused on the security aspects of it. So they were able to do exactly the things that they wanted to do with RISC-V. Had been doing, for the most part, with proprietary cores, but now it was better to move to RISC-V. So, estimating costs. So this trade-off thing of if you're going to build it yourself, if you're going to add custom instructions, how do you go and estimate those costs? Well, let me talk about processor verification as an example. I've mentioned you've got design costs, you've got verification costs, you've got the tool chain costs, you've got software porting costs. So processor verification, it shares some techniques with general SoC design verification. And that's good. So all the UVM stuff that people have been doing, all that experience helps. But processor verification is more difficult because of the large state space of the processor. It becomes a lot more complicated to do this. You need a good reference model to be able to work with this. So there are differences here versus what you're doing with the rest of the SoC. The processor IP companies, if we look at those historically, if we look at ARM or if we look at MIPS, these processor IP companies consider their verification flows and environments more valuable than the RTL itself. That never gets out of house. So these companies consider verification hard work and very important. That's an easy way of looking at it. Having the reference model, as I said, is necessary but not sufficient condition for processor verification. You also need a solid methodology. You need verification IP. You need other technology. You need things like functional coverage. I mean, it's verification. There's a lot that that goes into it. And some of the simple things that you think of, like doing signature compare or a post-simulation trace compare, is not sufficient for the complexities of a RISC-V core that you're going to be building, that's going to support interrupts, that's going to support privilege modes, and on like that. And then just one reference to a paper coming, I think tomorrow. Booting Linux or running other software is similarly incomplete from a verification perspective. One of our university partners, Harvey Mudd College, is going to be talking exactly about this sometime tomorrow afternoon. So how to estimate the processor verification costs? It's not easy. There's no simple formula or spreadsheet, but you're going to need to take a swag, a scientific wild guess at this, and you need to figure in all these things. And then you need to go and do the same thing on the design side, the same thing for the tool chain, and the same thing for other software porting. So just to sum up here, the RISC-V freedom, again, it's the key thing. The freedom enables domain-specific processors and motivates the increasingly obvious choice of RISC-V. How to choose a processor, the standard metrics, the IP ownership, the licensing cost, and the PPA. But with all the RISC-V implementations, the custom instructions, custom configurations are going to be used. And with these, you're going to need designing, verifying, tool chain development, software porting. And again, when making this processor decision, be careful to factor in the added complexity of the custom instructions and what you're going to need to do. So that's me. You can find me on LinkedIn. There isn't another Larry Lapides there, so I'm pretty easy to find. And for the next few days, I'm going to be around. We've got a booth in the exhibits, and tonight I hope you'll join Imperas after the general member meeting at 5 p.m. Party downstairs, bottom of the escalator, hang a right. Thank you.